So we have this pipeline that I think works pretty well. It's a pretty straightforward pipeline. You get a reasonably sized two-player zero-sum game. By reasonably sized, I mean it doesn't have too much hidden information. Then you find a team of about 10 RL researchers and millions in compute. And then after that, you have roughly a human level agent in your two-player zero-sum game. This is roughly the recipe that worked for Go and for StarCraft and for Stratego. So, if you can satisfy this desiderata in the middle, then you have what roughly looks like a working pipeline for building human level agents in two-player zero-sum games. As a caveat, you can also sometimes replace the middle of this loop if you have a training loop that runs at about 100,000 frames per second. And so we have this pipeline. It's not perfect, but it does kind of work, right? We've solved these games that seem quite hard to solve. And while we don't quite have the level of finesse with these kind of RL type things that we have for no regret solvers, like counterfactual regret minimization. And this, by the way, is what Dolly thinks lockpicks look like. So we do have this kind of rough hewn hammer. It's not the finest tool, but it does work. It is a hammer. It solves games, and that's great. And it's worked for us in a couple of settings too. So it's I'm not just just want to talk about things that DeepMind has done. We've used large scale multi-agent RL to solve problems in transportation. So this is part of a project called Circles. So on the left here, you have a stop and go wave, which you probably experienced in traffic at some point if you drive. And we kind of spun up this a simulator of a highway, and we did some kind of large scale RL on it. And you see kind of some of our cars on the right. They're the ones with the red arrows on them, and you can't see the green X, but they're the ones with the green X. And their goal is to kind of eliminate the stop and go wave by driving in a particular fashion. And the particular way that they drive is that they kind of open up these larger gaps that the wave dives into. And so about a year ago, we put 100 RL-based cruise controllers on the roadway, and it's called the Mega Vander test. And the basic thing that they did, so you can kind of see this wave forming at the bottom, where all the cars are at the top. We're going to have our RL controllers kind of keeping slightly different gaps, and you can see that they dissipate the waves. So for problems with kind of the right characteristics, kind of fast to simulate, or two-player zero-sum games, we kind of have a pipeline that works, and that's neat. The problem is outside of these settings. So there are settings where I would think that kind of large-scale game-solving techniques would be very natural, but where they don't really show up yet. So they're not really deployed. And I hope that if I'm wrong about this, somebody corrects me. But yeah. So for example, one very natural problem where you would kind of expect that you would use large-scale game solvers would be in generating multi-agent planners for autonomous driving. I think it's fair to say that the state of the art, or the things that are deployed on the roadway, do not really use equilibrium game solving as part of their stack. And similarly, we don't really generate controllers for human robot coordination through large scale game solving either. It's a lot more heuristic than that. So the question that like kind of keeps me up at night is, like, we have this amazing self-play toolbox. Why can't we just run it for general sum games and generate kind of amazing agents that are human level for these much harder problems? And there are a couple obstacles to progress, and we're going to talk. This talk is mostly going to talk about a couple of these obstacles. The first is incompatible equilibria. The second is a needing to define a set of equilibrium concepts that we actually try to solve for. And then the third, the most important of all, that we won't talk about at all because it's too hard, is evaluation. So what do I mean by these things? So by incompatible equilibria, I mean that self-play can converge to one of many equilibria, and those equilibria are not compatible with each other. So if I take self-play agents from one run and I take self-play agents from another run and I mix them, horrible things are going to happen. And a very natural example of this is which side of the road you drive. So self-play has no a priori reason to prefer one side of the road to the other. So if I run self-play once, I might get agents that drive on the right-hand side of the road. And by the way, here I mean by self-play, I mean agents trying to get to their goals without colliding into things. And if I run it again, I'll get agents that drive on the opposite side of the road, and those agents will only be compatible will only be able to drive in some countries and not others. You'll also see incompatible phenomena that are caused by cheap talk. So for example, if you give your agent access to a blinker and you kind of do self-play very well, it's going to learn to use that blinker to convey arbitrary information to other agents. So for example, you might see agents learn to do things like a convention that says, if I blink my blinker on, off, on, well, that means that you should wait for me to go. Also that I'm going right, and also that we should hang out later. If you do self-play properly, this does happen, this will happen. And that's pretty incompatible with how humans drive. So there's a couple of things that we could try to do to resolve this. So the first that we could try to do to kind of get around this is to try to come up with a reward function such that it reflects the exact deployment that we want, deployment environment that we want. And then we could run our solver on the reward function. We could look at that outcome. We could tune the reward function a little bit and then just keep running this loop. And so just to point out the limitations of that, once you enter this kind of reward function tuning phase, you run into some real challenges. You start writing reward functions that look like, okay, well, we should drive on the right-hand side of the road. We should stay lane aligned roughly. We should probably keep a distance from others, but not too much distance, the right amount of distance. It's obvious what that is. You should yield at stop signs, but not always, only when they're, clearly indicating that you should yield. You should give pedestrians right of way, but sometimes you should inch at them or else they're going to take advantage of you. So you can hopefully kind of see why once you start trying to pick out the right equilibrium by defining reward functions, you can wind up in a pretty rough place. The alternative, which I think is where a lot of economics spent a lot of time on, is you could try to come up with descriptive notions of what equilibria that you should solve for. So characterize the equilibriums, the set of equilibria that are sensible to play, and just try to force your agents to learn that sensible set of equilibria. So for example, equilibria that correspond to something, assuming that other agents are boundedly rational, equilibria that in some way rule out cheap talk, or equilibria that are possibly a best response to at least one other policy, or that don't break symmetries in arbitrary ways. And this is quite tricky to do because it's not totally clear which of these equilibria notions correspond to the one that humans would play if you were to try to play a game with humans. So my proposal, and what I'm going to talk about here going forwards, to unlock self-play is that we should focus kind of on data-centric settings. Like let's take a page from ML in some other ways. And so what do I mean by data-centric approaches? For example, you could try to just do large-scale behavior cloning. If you get data from the equilibrium and you get enough data from the equilibrium and you just mimic that data, you're probably going to do something like playing at the equilibrium. But in particular, the other two settings that I think are more exciting are to either focus on k-shot interactions, so settings where you get some number of trials to play with the other agent and you figure things out over time, or KL-regularization. So we have some amount of data and we're going to use it as a regularizer. And that's what we're going to focus on. So our setting is going to be the world where we have a little bit of data, not billions of miles of driving, but thousands of hours or thousands of hours of play. And this data will either be collected offline or collected over some number of trials. And I think that this creates kind of a spectrum of where you might want to live. So if you have no data whatsoever, then you probably do need to go back and you do this kind of reward tuning or descriptive selection of equilibria. And if you have infinite data, then you probably should do behavior cloning. And the question is what we should do in the middle. So we're going to explore what adding kind of self-play type methods atop of some reasonable amount of data gives us. And I think that there is a kind of a remarkable empirical fact about the world that I talk to everyone about that I can. And this isn't my work, this is somebody else's work, which is work that I'm obsessed with and think everybody should know about. And I thought this was kind of work that not enough people knew about, but then I realized it actually had almost won a best paper award. So clearly kind of appreciated in some way. And it's the fact that in the game Diplomacy, and Diplomacy is a strategic simultaneous move strategy game, which is a game that has an equilibrium selection problem. So there are multiple equilibria. You have to play the right one to beat humans. And you can see that by the fact that if you run self-play, and you take one of those self-play agents, and you play it against 6 humans, it gets crushed. Well, in this game, if you take a reasonable amount of data and use that as a KL, and you use that data as a KL regularizer in self-play, then you get human level play. This is just kind of a remarkable empirical fact. To me, I think this is kind of the first demonstration of overcoming equilibrium selection at scale. And it was also validated with human tests, which is very hard to do and very expensive. So I think this is just kind of a neat empirical fact that kind of shapes how I think about the world. And the particular way that it does this, given that we're short on time, I'm not going to go into the details, but it's basically you run self-play RL at each step. You kind of solve for the equilibrium of the stage game, and in particular, you solve it using this regularized hedge, where you assume that all the agents are sampled from a population that varies in how much KL regularization there is. And yeah, don't have time to focus on it. Thought I would have more time. So what I'm going to talk about now is not any kind of wonderful new algorithm or anything, but just trying to see how far this idea can get us. Maybe this is a pretty good solution to a lot of problems. And so I'm going to talk about a paper that a PhD student, Daphne Cornelise, recently put on the archive called Human Compatible Partners Through Data Regularized Self-Play. When we're thinking about what domain has some amount of data that we can use for KL regularization that's outside of games, well, we have driving. There are great data sets of human driving, thousands and thousands of hours of human driving. So it's one of the few multi-agent domains with data. And so what we're going to do is we're going to try to run self-play in Nocturne, which is a simulator we developed at Meta. And basically the goal in Nocturne is each agent wants to get to its goal. So we have these colored agents, and they each have a colored goal, and that's their target. It doesn't know the goals of other agents. And it also has this kind of partially observed view cone. So it can only see what probably a human would be able to see. And also it can rotate its head because I wanted them to be able to do implicit communication through motion, but that's for another talk. So we run self-play in this thing, and we can do a really good job on crash rates. So we can basically generate agents that never crash. We just run proximal policy optimization, which is a nice RL algorithm at scale. And then we take that agent, so it's going to be the agent kind of near the top. And we're going to play with some human agents just to see how it does. So it's going to get to its goal. Yeah, but maybe not in the way that we want it to. So this, we immediately see this kind of incompatible equilibrium technique. Learns to drive in a way, but it's not the way that humans drive. So we're going to do the simplest thing that we could possibly think of. And that's just to add a KL regularizer on top of our PPO loss. So we're going to take our PPO loss and we're going to weight it by some value lambda, and we're going to add a weighted KL loss to it. And then just because we don't want any of the results to be a function of some kind of reward that we've added, we're going to use no reward shaping. So our reward is just going to be sparse. You get 1 if you made it to your goal, 0 if anything else happens. So here, this KL term is both going to ostensibly be helping us with equilibrium selection. It's also going to be filling in for some of the rewards that are, and laws that are clearly missing in the reward term. So we take this, we pre-train a 50% goal rate reaching behavior cloning model, which is a very bad regularizer model. You can do much better. We just haven't done that yet. We take about 30 minutes of data. And again, we could do better by taking in more data and building better IL models, because when you regularize with a bad model, you also pick up some of the model's bad behavior. We're going to train on 200 scenes, then we're going to eval on 10,000 scenes. And this is just kind of 9 representative scenes from Nocturne. So how does this do? So there's a couple of metrics that we would probably want to look at to evaluate if the agents that we've trained are any good. The first we call GC-ADE. So average driving error is kind of a common metric used for measuring human likeness of driving agents. Basically, you look at the trajectory you took, you look at the trajectory that the expert took, so you have some data from an expert, and you kind of sum up the difference between those two things. We're going to look at GC-ADE, which we distinguish from ADE because we actually know the goal. So we don't have to figure out where the goal is. We just are trying to drive to a goal. And there we see kind of a small trade-off as we increase the value of lambda from, so over here, lambda is basically 100%. We're fully VC. Over here, sorry, lambda is 0. So this is full PPO. And along the way, we have a spectrum sweeping from PPO to behavior cloning. And for fairly small values of lambda, we can achieve fairly high goal reaching rates without giving up too much in GC-ADE. We can also look at kind of steering error, because you could follow the same trajectory, but you could do so very differently, for example, very hercules-jerkily. And there we see almost no trade-off at all. So basically the steering error basically looks like we steer like a human does while achieving the same goal rate as PPO itself. The other things we might care about for evaluating the quality of our agents is how they do in self-play. So we would probably hope that if the algorithm is working correctly, then agents should be closed loop effective. So if we play them with each other, they should achieve their goals with high goal reaching rates. And so over here, we have kind of the self-play performance. In blue, we have the behavior cloning agents. In orange, we have default PPO agents. And in purple, we have default PPO agents. And then in orange, we have our HR PPO agents, so the PPO with the regularizer. And we achieve about a 95% goal reaching rate. So, 19 out of 20 agents make it to their goal. The other thing I want to mention is the reward curve is still ticking up. If we ran this for longer, they would all get to 100, or they would get to the maximum that's possible. Our cluster just timed us out. And then the last thing we would care about is maybe this kind of like log replay proxy, which is also a common driving metric. So in log replay, we're just every agent but one is going to just replay logs collected from the real world. So basically they're on rails. And then one of the cars is going to be controlled by our agent, and it's going to try to drive through these non-reactive agents. And there we see on the right a degradation from how we do in the self-play setting. So we go from about 95% to about 83%, but a larger improvement than the drop-off that PPO itself, so without the regularizer, experiences. And I want to dive into these numbers a little bit because they're a little bit deceptive. So if we look at how our agents do as a function of how interactive the scene is, we can where we have some kind of proxy metric for interactivity. We can see that HR PPO, so our regularized PPO, is basically flat as interactivity increases, whereas once we get to really interactive scenes in log replay, the PPO agent just starts to fail at really high rates. And if we dig into like what those failure modes look like, it kind of we can kind of see that our agent is actually extremely good at coordination. Its remaining failures are basically properties of the data set and properties of training. So in about a third of the data set, a third of the failures, the goal is actually unreachable. In a third of the failures, we just haven't trained for long enough, so our agent is not great at like doing really sharp steers. And then in a third of them, there is a genuine coordination failure. So here, this agent over here thinks that in self-play, that car in front of it would move out of its way, and in the reality, it doesn't because it's non-reactive. There also, you can see really stark qualitative differences between these two settings. So here we have our like self-play agent from before, and here we have what it looks like after adding a little bit of regularization. Super boring. It's just drive straight, and then it doesn't turn. Great. You can also see things like, so on the left, like pure self-play, they have this kind of overall coordinate equilibrium where they don't really wait for each other. And over here on the right in HRPPO, like you can see this white car is kind of waiting at the stop sign to enter the roundabout. And it kind of, one more last example I like is, here in the left on pure self-play, it doesn't think to wait for the other car. And over here, it realizes that the other car is inching out and it should wait for it. So I'm gonna just skip this section and talk a little bit about future work. So there are many questions that are unresolved here, and I'm just gonna list off a few in case anybody has questions about them, wants to talk about them. So one, our regularizer is a very bad policy. Some of our failures are clearly due to our regularizer. Like we can see that our BC policy will sometimes scream, smash into a wall as fast as you can. And because of the particular way you regularize, there's always a non-zero chance that you obey that instruction. As I mentioned, there's really nice result in diplomacy, and in diplomacy, they use this particular algorithm called dill pickle that I didn't get a chance to go into. But how much does it matter to use the particular form of regularizer that was used in that paper versus just naive additions of regularization? And then there's so many open problems in how you actually should incorporate the data. So one, you could add search on top and try to do online adaptation of the regularization component. So you could learn a regularization conditioned policy and vary that regularization. You could kind of move to the adaptive setting and think about how to do search and planning in K-shot games, where instead of just having the data offline, you're also allowed to, you have some trials where you're allowed to collect data throughout them. And there's also the question of scaling with dataset size. So, how many hours do we need for this to possibly start working really well? And, hopefully this is useful for more than driving, and there's some other setting you're thinking about that this could be helpful for. So in summary, maybe incorporating a little bit of data as a KL cost empirically resolves equilibrium challenges, maybe, TBD. It seems to scale for us so far, but we don't really know what the limits of it are. So we'll see. There's still so much left to do. So I want to end by thanking the members of the eMERGE lab. When we came up with the acronym for eMERGE, we had something really good, but we can't remember what it is. So now it's just that until we think of something better. So yeah, thank you. And any questions?
Great job, Eugene. So we have time for some questions for you. You can come up to the mic if you.
Okay, very nice talk. So I was wondering, when you have this human regularizer from the human, so it can happen sometimes that you try to imitate the human in some way, and then this will give worse performance than just giving RL an objective in the reward function. So how do you balance doing like the human or socially aware or these things versus the performance in the task? Because normally this opposed in some way.
Yeah, so adding that regularizer forces you to sometimes take the suboptimal actions that come from the imitation policy. Once you get that imitation policy up to a certain quality, then the probability of taking those bad actions is pretty low, but they're still there. So, at least in the context of gameplay, this doesn't seem to be a problem. But I don't fully know. I think one thing we've thought about is doing like uncertainty quantification, then trying to figure out like when we should lower the regularization weight. The other option is to add kind of search on top to kind of filter out some of those bad actions. There's some open options, but we don't know what the best one is.
Okay, thanks.
Thanks very much.
So I want to ask, so this regularization is mainly used for tasks that is very human-centric, right? Because we are trying to follow the examples of the human. Because when I heard of like RL, usually people use it to like achieve like superhuman level performance. But in these types, we would want it to be as human-like as possible.
Yeah, so in this setting, we're using it to try to make things behave a little bit more human-like and play compatible with the equilibria that humans play, if you believe that humans play equilibria. But you could also imagine in fully autonomous settings that there is an existing equilibrium that fully autonomous agents play, and even there, even though those agents are superhuman, you still have to play compatibly with their equilibrium. So it's just a general problem of general sum games. It's just that in the case of playing with humans, it looks like play like the humans.
But then, if let's say, so the superhuman level comes about because they kind of like discover a superhuman equilibrium.
Right. So actually, in this case, even here, the resulting agent is not a clone of a human. It could be a superhuman player. It's just that we don't have that yet. Right. Like in the case of diplomacy, the thing that comes out is not a clone of a human. It is a better than human player. There's nothing in this equilibrium in this game solving procedure that prevents you from making better than human actors.
Great talk. I just had a question. So in the first few slides, you showed this picture of human-robot collaboration, like a warehouse setting. And so one distinct difference between that and autonomous driving is that you're kind of interacting with the same agents in a closed environment. So I guess, is there anything about kind of this interactive data collection with the same agents that you could utilize to improve the overall closed-loop performance? Maybe you're interested in some higher level metric, as opposed to just autonomous driving, that there's a very low chance that you're interacting with the same agent over an extended period of time.
Yeah, I think that's a great question. So one obvious variant of that would be, okay, you slowly collect that data over time and your regularizer moves towards coming from that data, right? But also now that you're in that setting, you can think about actively exploring and trying to, collect better data, or, you have some pre-computed set of equilibria and you're just trying to pick out over which one you're actually currently playing or something like that. There's a huge number of options for things you could do when you're in the repeated setting, which I think is really exciting. Yeah, I think it's a great setting to study. Great.
There's a question online. Can the human regularize PPO and PPO compare in terms of constraint violations?
Yeah, so it's kind of naively, it seems very simple to like compute the constraint violations. Like, did you go past the stop sign when you shouldn't have? It's actually pretty annoying to do in our simulator. So qualitatively, constraint violations here are laws. Qualitatively, the HR PPO agents violate laws far less often, but we're not actually computing how often they're doing that. It's just a little hard to do in our simulator, which we'd love it if someone added that feature.
Great. This was a great talk. Lots of good questions. That would be like here. Thank you so much, Eugene. Awesome.
Thank you all very much for having me.